Alright, hello again and welcome to another instructional video for this chemistry course. We have been looking at naming compounds recently. We looked at naming ionic compounds and then we focused our attention on molecular compounds. Well, today we're going to be looking at naming acids, and the reason why we spend a little time talking about naming acids, even though there's going to be a whole unit about acids, we're going to be talking about the properties of acids and how you identify an acid, how acids react. That's for later on. But we're going to talk a little bit about just naming acids because acids are a little bit unique. They are used in lots of different areas, and so they have a little bit of a different naming process. You can see here that when you have an acid in its solid form, in its molecular form, it is a covalently bonded molecule. So you would think, well, we just name it like our previous video and name it using the molecular compound system. But when you have an acid and you put that acid into water, the water is going to cause that solid to form ions. And so as a result, one of the ions that is produced is always going to be H+. You will most of the time, predominantly you will see H in the formula for an acid, and when that acid is put into water, that H plus is immediately, to a certain degree, for strong acids it's a greater dissociation, for weaker acids it's a lesser dissociation, but you're going to see that H plus dissociate itself from the other ion. It's going to break apart from the other ion, and that H plus is going to combine with a water molecule to form H3O+. So it's an H plus and water. When you put that solid acid and you put it into water, that H plus ion and the acid is going to combine with water to make H3O, and it's going to have a plus charge on it. There is an ion in solution, and this ion right here gives acid its properties. So it's rather unique, and as a result, we have kind of a different naming system for acids. Let's look at Model 1 here. We have acid formulas here. We have the name of the acid in aqueous solution. By the way, it is an acid once it is put into an aqueous solution. Aqueous solution meaning water. Okay, that's when it becomes an acid, because that is when this hydronium ion is created, H3O+. And then we're going to identify how many of those hydronium ions we have, and we're going to identify the anion, the other part of that formula that is going to make up that acid. Okay, so let's answer these questions using Model 1. Complete the cation and anion columns in the table in Model 1. Be careful to show the charges of the ions. So we already have been told that the H+, when you take a solid acid in its solid form and you put it into water and you form an aqueous solution, the H+ that is in that acid is going to join the water molecules to always form H3O+. This is called hydronium ion. So we're looking for how many hydronium ions are we going to have, and the hydronium ion is your cation. So if you've got H, there's your HCl, that H is going to combine with the water molecule and form H3O+. Here we have H again, it's going to form H3O+. Here notice we have H2S, two H's, so each H is going to split apart, and each H is going to find a water molecule, or a water molecule is going to find the H, and you're going to form two separate hydronium ions. And then here you're going to have again just the H3O+, hydronium ion. The corresponding anion is the second part, basically, of these binary acids. Binary acids, two elements, right? So you've got chlorine, bromine, sulfur, and fluorine here. Those are the second parts of these acids. And we know what the charge is going to be just because we know that H is always going to be a +1 for acids anyways. And so our corresponding anion here is the chloride ion with a charge of -1. The corresponding anion for the HBr is going to be Br with a -1. And here, notice in this one, we need 2 H's for the to match up with the sulfur. So that must mean that sulfur has a -2 charge on it because each H is a +1. And here HF, that must be fluoride ion with a -1. Why does a hydrosulfuric acid contain 2 hydrogens? Because it is combined with the sulfur, which is a 2-. Okay? They must form neutral compound. Okay? So to form that neutral compound, you're going to need 2 H pluses to combine with the 1 S -2. It's that simple. Remember that from previous videos, I hope. Look at the formulas and names of the binary acids in Model 1. So we got formulas given to us and the corresponding name there with it. What prefix is used at the beginning of the name of all binary acids? You should see here we've got hydro, 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 because we've got hydrogen in every single one of these formulas. Okay? And what suffix is used? Every one of these is going to end in IC. IC, 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 ic. The prefix bi means 2. We've seen that when we talked about molecular compounds. Propose a reason that the acids in Model 1 are all referred to as binary acids. That's because they've got 2 elements. One of the elements is always going to be hydrogen plus something. Probably a nonmetal like chlorine, fluorine, sulfur, as we've seen here in Model 1. Okay? Write a rule for naming binary acids. Basically, you're going to start with hydro, always, plus you're going to have then kind of the root part of that nonmetal, the root name of the nonmetal, and then you're going to add ic at the end. And often, just to make sure it's clear, you're going to write acid. Okay? So, hydrochlor, there's the root part, chloric acid, hydrobrome, there's the root part, ic acid, hydrosulfuric acid, and hydrofluoric acid. Okay? Here's our second model. Now we are looking at ternary acids. And remember, we kind of looked at ternary molecules in a previous video, and there was a little bit of a deeper process that we need to go through to name these. And so, like with acids, if there are ternary acids, meaning there are 3 or more elements, if there are 3 or more elements, then we're going to have to kind of clarify a little bit more in our naming process. These are also called oxyacids because you're going to see oxygen in all of them. There's your oxygen, 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 in all of these, so that's why they're also called oxyacids. They all have 3 or more elements in them. Here we are given the formula, here we're given the name. Cation is going to be identified. For all of these acids, it's going to be the hydronium. In some cases, there may be 2 of them or 3 of them. The polyatomic anion, here, we're not just going to have a single monatomic ion, anion, we're going to have a group. Remember we talked about polyatomic ions? Here is your group. There are groups now that are bonding with that hydrogen. So we're going to identify those polyatomic anions. And then we're going to write the name of that anion that we have seen previously. Okay, so we're bringing in previous knowledge here and combining it with the naming of these acids. Look at the formulas of the ternary acids in Model 2. How are the ternary acids different from binary acids in their structure? Well, they have two or more elements. In this case, they all have oxygen in them. Okay? So they have hydrogen, that's a given for most acids, plus then another non-metal, and then plus the oxygen. Okay? What number do you think the prefix ter refers to? So that would be, oh, sorry, I said 2 or more. I meant 3 or more up here. I'm sorry. 3 or more elements. 2 is just binary. My apologies. Okay, 3 or more elements. 3 or more elements. So ter is going to mean 3. When ternary acids are mixed with water, ions will form. We already mentioned that. Fill in the table above with the formulas and names of the anions. Yep. So the anion is just going to be the second part of this. And we know what the charge is going to be because we know H is always going to be a +1. And when that H joins up with water, you're going to get the hydronium, H3O+, which is still a +1, by the way. So here you've got the ClO3, which is just the second part of this acid formula, and it must have a charge of negative because it's just with one H. It's just bonding with one H. Here, this group, the SO3, is bonding with two H's. So the SO3 must have a charge of -2, and it is bonding with two different H's. So it's going to form, those two H's are going to form two different hydronium ions. Here again, you've got two hydronium ions that are going to form, shown right there, that subscript. So that must mean that SO4, the sulfate ion, has a charge of -2. Here we're going to have three different hydronium ions that are formed, and you're going to form the other ion once it's put into water. This other ion here, the phosphite, is going to have a charge of -3 on it because there are three H pluses that are bonding with it. PO4 has a -3 charge. How do we know? Because it's forming three hydronium ions from the three hydrogens that are in the formula. And we've got here, we're going to have hydronium along with the nitrate ion. So this NO3 must have a charge of -1 because it just has one H. And here another hydronium, of course. And we got the nitrite. Here we've got two hydroniums, and we've got the carbonate with a 2 negative charge on it. Okay? Examine the pairs that contain sulfur, phosphorus, and nitrogen. Each pair has one acid that ends in IC and another that ends in OUS. These endings are related to the name of the polyatomic anion found in the acid, ate or ite. Complete the statements below with the correct acid name ending. So, with binary, that was model 1, binary, the acids always end in IC, ic. And that is also the case for many of these. But if the acid is using the ate anion, it's going to end in OUS. So let's look at this a little bit more. I'm sorry, if it's using, my apologies, if it's using the ite anion, the ite, ITE, polyatomic anion, it is going to end in OUS. So this one right here, this is ending in IC because the hydrogen is bonded with the chlorate ion. Here, this is sulfurous. Let's compare it down here. Let's go here, this one first. Sulfuric, because the H is being combined with the sulfate. So if the anion group, the polyatomic anion, would be the ate anion for that particular nonmetal, in this case sulfur, then it's going to, as an acid, it's going to end in IC. But if it's sulfurous, that means it is using the ite anion. So this would have been using the sulfite, which is SO3 with a charge of -2. Okay? Phosphite is going to be named phosphorus acid, whereas if you're using the phosphate ion, which is PO4 -3, then it's going to end in phosphoric acid. Nitric, that must mean we're using the nitrate ion, and nitrous using the nitrite. Carbonic, that must mean this right here, this polyatomic ion here, polyatomic anion, is the carbonate. Okay, so let's just answer this question. If the polyatomic anion ends in ate, 8, sulfate, chlorate, carbonate, the acid name ending is going to be IC, as we saw with the binary. If the polyatomic anion ends in ITE, ite, sulfite, nitrite, then the acid name ending is going to be OUS. That is new. That is different. That is different than binary. This is where so you have a different ending in the case where you're using the ite polyatomic anion. If the prefix hydro were used to name a ternary acid, what problem would this create when naming HClO3? So, if we said hydro, notice none of these have hydro at the beginning. That's something that's different as well with ternary. That's not hydro anything. That's only for the binary acids. So, it's saying if the prefix hydro were used to name a ternary acid, what problem would this create? Well, if we use the hydro, if I said hydro, let's just write it out. Hydro, and this is the 8, ClO3, that's the 8 ending, that's the 8 polyatomic anion. I would name this hydrochloric acid. But that's not the formula for hydrochloric acid. Hydrochloric acid is just HCl, binary. So I am going to make sure that I differentiate between the binary acid that has chlorine in it and the ternary acid that has chlorine and oxygen in it with the binary I'm going to have hydro and it's going to end in IC, but for the ternary acid that has hydrogen, chlorine, and oxygen, HClO3, I'm not going to write the hydro. So this is just chloric acid. Okay? We have to make sure that we know the difference in these cases, so the naming is just a little bit different to know which one we're talking about. So write a rule for naming ternary acids. We kind of already have mentioned that. Let me just point out a few differences. We've already mentioned them. For ternary, you do not use hydro, no hydro, and you have to take into account ic or us. And as we mentioned up here, you're going to end in ic if the polyatomic anion is the 8 one, and it's going to end in OUS if the polyatomic anion is the ite one. Okay? Alright, predict the formula for chlorous acid. Well, let's go back up to Model 2. Because we have a chloric, and that's using the chlorate polyatomic anion, and that is ClO3 negative, well, the chlorite anion is ClO2 negative. It's always one less oxygen than the 8 polyatomic anion. So we're going to take this polyatomic anion and combine it with an oxygen. Just one because the charge on this is -1. So it would be HClO2. OUS because we're using the chlorite anion. Circle the acid below that would be named beginning with the prefix hydro. Hydro, here it's really simple. If you see hydro, guaranteed it is a binary acid. So, 2 elements, 2 elements, the others all have 3 elements. These 2 right here would start with hydro. Hydrofluoric, HF, hydrosulfuric, H2S. Okay? Let's go on to the extension questions. All right, we're already there. Model 3 is looking at halogen oxyacid acid families. So halogens, that is the group that has chlorine, fluorine, bromine, iodine. Those are your halogens, okay? Oxyacid means it's going to have oxygen in it. So if you look here, we have HCl and O. There's your hydrogen, so it's an acid. There's your nonmetal chlorine, which is a halogen, and there's your oxygen. And what we're going to look at here is we're going to look at kind of a family of acids. All of these have hydrogen, chlorine, and oxygen, but in different ratios. And we're going to realize that, we have to somehow delineate how many oxygens are in there by using the name. The name is going to help us know relatively how many oxygens are there, and that will kind of show up in the name as we go through this. Notice that we've got in all of these, you've got the base of CHLO, 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 CHLO in all of those to designate that it is chlorine. Here's our hypo, but it's not hydro. I don't want you to get mixed up. And here we have a per, those are new. These are all ternary acids. But now we have this whole family here, so we have to make sure we have a naming system so we know which is which. Write the formulas of the cations and anions for each acid. So all of these, all the way through, just have one H, so all of these are going to be hydronium. All the way through, all of these are hydronium, all the same. The anion, we just look at the second part here. ClO4, ClO4 with a -1, ClO3 negative, ClO2 negative, and ClO negative. All those are -1 charge because they're all combined with just one oxygen. Here, I'm just going to continue on. I've got the BrO4, must also have a -1 charge. IO3, -1. FO2, -1. And we are given the IO, -1. Okay? So, right here, we're going to use this as our guide. If in that family of acids, whether it is chlorine or bromine or iodine or fluorine or whatever, the one that has the most oxygens is going to start with PER. The one that has the fewest oxygens is going to be hypo. And then in between, we've got the IC and we've got the OUS. So we already saw the IC ending and the OUS. We know that this one is the 8 ion. This is the ite ion. Now we've got one just on either side of these 8 and ite. So we've got a perchlorate and we've got a hypochlorate, okay? Or hypochlorite, my apologies. So this ion that is being used here, the ClO4, is called perchlorate because it has one more oxygen than the chlorate. And this is hypochlorite because it has one fewer oxygens than the chlorite. Okay? Just something you got to know. HBrO4, so if we were looking at this, this is using the perbromate. We are told that. So this must be perbromic acid. And here we are using the IO3. I think that is iodate, if I'm not mistaken. So that would be just iodic acid. HFO2. Oh, you know what? Let's continue to go through some of these questions here. I'm kind of getting ahead of ourselves, and haven't been answering these questions here. So let's go down here to 14. Consider the names of the oxyacids in model 3 that contain chlorine. All halogens form similar oxyacids that use the same naming convention. Fill in the names of the halogen oxyacids to complete the table. So we did that here. We use the names of halogens to complete the table. All right. The table below includes both binary and ternary acids using what you have learned in this activity. Fill in the missing formula and name for the anion in each acid and give the formula of the acid. Okay, we're going to come to this in a little bit because we've got a mix here of binary and ternary. Okay, so let's finish this up. HFO2, if this is our fluorite, if that's fluorite, it might be hypofluorite. I'm not sure about that, but let's say it's fluorite, then this would be your fluorous acid. Okay? Here we're told this is hypoiodite ion, so then to name this you would call it hypoiodous acid. Okay? Alright, here's some good practice for us. We have now a table where we've got a mix of binary or ternary acids. And we need to use our system that we just learned now today to use these names and identify the anion and then come up with a formula. So hydro, not hypo, this is hydro. As soon as I see hydro, I know it is binary. And the second part here is iode, that's iodine, and it ends in IC. I know this has to be H and I. The anion is going to be on my H+, and of course when that combines with water, you get the H3O+. I'm going to put that in parentheses. The anion is just the I negative. The iodide anion. Chlorous, there's no hypo. If there's no hydro. No hydro. If there's no hydro, then you know that it is going to be ternary. Okay? Hydro is for binary, no hydro, ternary. So as soon as I see there's no hydro prefix, I know this is ternary, and I've got chlorous, so that means it has the 8 anion, so it's chlorate, and if you've forgotten chlorate, you can look back up above, but I'm pretty sure it's ClO3. Okay? And again with the H+ here, so it's going to be HClO3. Hypo, not hydro, hypo, so that must mean it's ternary. Bro, it's bromine, and OUS. So if we look up here, the perbromic had 4, so that means that's the perbromate that has 4. That must mean the bromate, just bromate, has 3, and the chlorite has 2, and the hypo must just have 1. Okay, kind of like the hypoiodite here. So this would be H+, this would just be the BRO, and then HBRO. Phosphoric acid. Phosphoric, there's no per, there's no hypo, it's just ending in IC. So the phosphate ion here is just going to be PO4, and this has actually a 3 negative. If you don't remember the ions, the polyatomic ions, refer back to a table of some type. Okay? So this would be your H+, and the phosphate, so this would be H3. We're going to need 3 of these here. 3PO4. Sulfurous ends in OUS, so that would be using the sulfite, that is SO3, has a 2 negative charge, so that would have to be combined with 2 hydrogens. This is our sulfite, SO3, 2 negative, and therefore we'd have 2 hydrogens. Okay? Alright, that wasn't so bad. You just have to know how to name acids, and know that if it's binary, it's always going to start with hydro, and then the root part of the non-metal name, it ends in ic. If it's ternary, we have to use our naming system that we discovered right here in Model 2. Okay? Alright, I hope that's helpful. This was just a quick video on naming acids, and we've now kind of wrapped up the unit here on naming, and we are going to talk a little bit now about the structure of these compounds as we dive a little bit into the molecular geometry of compounds in our next video. Alright, I'll see you there.